So let's start our today's session.
Mm-hmm.
And in our today's session, we are going to look at the second part of electric charges and fields, to be precise.
Mm-hmm.
In the last class, we talked about electric charge, to be precise. But today, we are going to first understand that how those electric field lines look like, what exactly originate from the charge.
Mm-hmm.
So we'll be talking about that field. We are going to talk about that how that field can be calculated. We are going to look at the configuration that how the field originates, and later on we are going to talk about its properties. So
Mm-hmm.
this is the first section of this today's class, and next is electrostatic potential energy or electric potential energy. So everything related to the potential energy thing, we are going to talk about it.
Mm-hmm.
So in order to relate these two things, or like all the things which we have studied so far, just remember this way that in physics, first we are going to define some kind of force. And the classical physics given by Newton says that whenever there is a force, there must be some displacement. Like, for example, if you push something or pull something, that object is not going to stay at its place, it's going to displace. And if there is a displacement, it means there is some work done. Or I can
Mm-hmm.
say that this force has done some work on the object because of which that object has displaced.
Mm-hmm.
And later on, we simply relate this thing with energy as well. Like, if I am capable of doing work or like by pushing an object and displacing it by its position, so it must be possible that I have energy to do that work.
Mm-hmm.
So whatever work I have done, that work is something because of that I had. So that energy is something which is sometimes called potential energy. And in every topic where we are going to learn about some new force, first, we are going to define the work done by that force, and then we are going to calculate the potential energy of that force. So, if you
Mm-hmm.
relate the same in this chapter, first we defined electrostatic force in the very first lecture. This electrostatic force must be capable of displacing charge by its position, so there must be some work done by this force. And later on in this class, we're going to relate that work done by the force with energy. So it simply means that the particle or the object must have some energy that
Mm-hmm.
because of that only he or she is able to do some work, and that work, and in order to do that work here the force which plays the role is electrostatic force. So
Mm-hmm.
this is the basic procedure which we are going to follow in almost every unit, you can say.
Mm-hmm.
So let's start this lecture and talk about all these things in details. So the very first question which we are going to answer after this lecture, that why lightning is falling on this particular building, not the other ones. So we're going to find out the reason that why specifically this only. Because if we are going to know the reason, we can protect the other buildings from being hit by the lightning. So that is what most of the buildings, when they are going to construct, does in order to protect it from lightning or even say
Mm-hmm.
thunderstorm. So first thing is, what is electric field? Like, you need to understand this thing that whenever there is a charge, whether it is positive or negative, because of this charge, there must be some kind of field, and that field is regarded as electric field. Electric field is a vector quantity. Vector quantity means this is the field which must have some direction as well, along with the magnitude.
Mhm.
So that direction and magnitude both will affect, or you can say both will be responsible for displacing this charge in some direction. So we define electric field as the region which is being surrounded by the charge in which its electrical effect can be experienced. Now, what does it mean by electrical experience? So suppose if there was a charge and because of that charge, there was some electric field. So in this electric field, if I put a charge, so this charge must be experiencing some force, and that force is nothing but electrostatic force. Similarly, if the same nature of charge was present near negative charge, then the force experienced by that charge will be in this direction. Like you can assume if it is a positive charge and it is present in some positive charge electric field, so the force which is going to experience is repulsive force, and because of that repulsive force, the object or the charge is going to move away from it.
Mhm.
Similarly, if a positive charge is present in some negative charge electric field, the force is going to be attractive and it will be responsible for pulling that charge Q towards this negative charge. Like simply positive opposite attracts and similar repel. This is what it signifies.
Mhm.
So it is called electric field of the given charge. So electric field is always defined for a single charge or even a multiple charges. But you can say electric field is defined for charge only. Now the question is how can we find this electric field? What is the magnitude of electric field? What is the formula of electric field? So let us understand it in a very simple way, assuming the last example. So I suppose that there is some positive charge which is being there in the surroundings. And because of that positive charge, there was some field lines. In this positive charge, we have placed a small test charge. I'm calling this charge as test charge because I want to find the magnitude of electric field originating because of this positive charge. So test charge is something which will help me to find out that field strength and also
Mhm.
regarded as field intensity. So this is a positive charge and I placed a test positive charge to be precise. So in which direction will this test positive charge experience force? As positive, it will repel, so force will be in this direction.
Mhm.
So electric field intensity is somewhat defined as that it is force experienced by the unit positive test charge. And if we substitute the value of force, which we studied in the last class, that is Coulomb's law, what
Mhm.
was it? It was K Q1 Q2 by R square. So I can write the electric field as this.
Mhm.
So this Q will cancel out this Q, and the electric field originating from this capital Q charge is given by this relation. What is the
Mhm.
force? K Q1 Q2 by R square, where R is the distance between the charges. So electric field intensity is somewhat KQ by R square.
Mhm.
So this is the formula of electric field, and we are going to calculate the magnitude of electric field using this relation only. So it is defined as force per unit charge exerted on a positive test charge at rest at that point. So this is the technical term, technical statements. Now, how the electric field lines actually looks like. So basically, first of all, these are the imaginary curves. Imaginary curves, or you can say if there is some positive charge, if there is some negative charge, so electric field will originate from positive and terminate at negative. So
Mhm.
during that connection between positive and negative electric field line, They generally forms that curves. Straight lines are very rare, but curves are general. So we generally observe that they are imaginary curve tangent to which will give the direction of electric field. So at any point, if we want to find the field line's direction, what we do is we simply draw the tangent to that field line, and that at any point, if we draw the tangent, this will give us the direction of electric field line. Like if I assume it to be this, then field line direction is supposed to be here. I assumed
Mm.
it to be here, electric field line direction is supposed to be here. It is non-mathematical way of studying. Tangent gives direction of field. Let me explain it to you here. So electric field line must be here. Electric field line must be here. Electric
Mhm.
field line must be here.
Mm.
Similarly for this, it must be here. So basically, every time you have to draw the tangent, and that tangent will give us the direction of electric field line.
Mhm.
So for positive charge, direction is away from the charge, like it is going away from it.
Mhm.
Electric field lines are away from the positive charge, like this. For negative charge, it is towards the charge, like this.
Mhm.
So the diagram shows the representation of all this. Two electric field lines cannot intersect each other, the most important point. Because if they were supposed to do so, then at a same point, electric field line is supposed to be possessing two directions. And
Mhm.
one quantity having two directions is not possible. So this is something you need to remember that they cannot intersect ever.
Mhm.
Why? Because it must possess two directions, which is not possible.
Mhm.
Electrostatic field lines are perpendicular to conductor and no electrostatic field line inside the conductor. Another important point or important property. So suppose if I have a conductor and this conductor is supposed to be placed in external field like this, then electrostatic field line must not pass through the conductor. Like inside there is no field line. This is the most important property of the conductor. So this is the reason why it was supposed to say that whenever you are outside and there is lightning, so just try to cover yourself. Because if you cover yourself with some sort of shed, so that
Mhm.
electric, that lightning, if it may strikes you, it will directly go into the earth. So it won't
Mhm.
strike you if you are under some shelter. So because of the conductor, they might try to induce charge on the surface of this conductor by doing this. And they also used to enter into it, or you can say terminate into it. Continue curves in charge free area. They will always forms a continuous curve, like you can say a very smooth wave. They never form any steep lines, straight lines, generally curves.
Mhm.
Electrostatic field line is conservative in nature. Another important point. Conservative means for such force, potential energy is defined. Like this is something which we used to study in grade 11. There are two
Mhm.
types of forces, conservative and non-conservative forces. Conservative forces are those forces for which potential energy is defined, whereas non-conservative forces are those forces for which potential energy is not defined. So what is defined for them? For them it is kinetic energy. So potential energy is defined for conservative forces only, and the conservative forces are only four in nature, like four in number.
Mhm.
So you need to always remember them, that what are these conservative forces. The first is electrostatic force. It is conservative in nature. Then we have magnetic force as well. Magnetic forces are also conservative in nature. Then we have gravitational potential energy, the gravitational force.
Mhm.
That is also conservative in nature. Last, spring force. So only for these forces, potential energy is defined. For rest, there is only kinetic energy. Like, let me give you the
Mhm.
example. There is a force called frictional force. So for friction force, we don't define potential energy, we only define kinetic energy. Also, you can assume that there is some air drag, viscous force, whatever other type of force that might come to your mind. It is non-conservative, and for those forces, only kinetic energy is defined.
Mhm.
So you must remember these forces. Now, another important statement: crowded lines means electric field is higher. So suppose if I consider 2 points, point A here and point B here. So I
Mhm.
must say that electric field at point A must be greater than electric field at point B.
Mhm.
Because if there is more crowded region, then it was supposed to have a great field at that point.
Wait, is it
So
because like um are the lines in A closer than in B?
yeah, because somewhat number of field at a particular unit area increases, so the field intensity also increases. If number
Oh.
of field lines through a unit area is less, then field strength is also supposed to be less.
Mm.
Next, we'll be looking some electric field line in different cases. These cases are some. If I had two opposite charges, so if there are two opposite charges, then field line is supposed to be like that. Like for two positive charges, field line never meet.
Yeah.
If they would have meet, they would intersect, and intersect is something which is not possible for two field lines.
Yeah.
So they will just pass away from them like this. They never meet.
Oh, okay. Got it.
So for two similar charges, like positive, positive,
Mhm.
they are not supposed to meet, as well as for two negative charges,
Mhm.
like this. This is different. This is positive
Positive.
and negative.
Mm.
So for opposite charges, the field line is supposed to be initiate from one and terminate into other.
Mhm.
But for two positive or two negative, it is not like that. This is
Mhm.
opposite charges. And two opposite charges of equal magnitude is regarded as dipole. It is another physical quantity, and for
Mhm.
such configuration, we define dipole moment.
Mhm.
So we will talk about it. Electric field line has tension that try to get its end together. So there must be some tension which tries to pull them together as much as they can.
Mhm.
Then some different quantity. This is a line charge. Line charge is something like you can say wire. A wire which is positive charge, positive in nature, is supposed to be emitting electric field from its structure, supposed to be this way. Like this is something which is in 3D.
Mhm.
So this is called line charge, and for line charge, field line is supposed to be like that. Next we have plane surface. So suppose I have a sheet, it is some positively charged sheet, and this sheet must be emitting field lines perpendicular to its surface like that, which is shown by this diagram.
Mm-hmm.
So this is something we call surface charge because of surface charge. So it is something we called planar. So field lines are planar. This is what we
Mm-hmm.
explain. Next, we have to understand that what is electric field and induced electric field. Electric field is something which we already defined, like force experienced by the unit positive test charge is something we call electric field. This electric field is due to a charge which might be present on a conductor or might not be. So it might be an independent charge also. But
I'm
induced
guessing
field,
induced is like it doesn't have a charge and you have to like
yes.
okay.
So suppose there was a conductor, but this conductor is neutral. What do you mean by neutral thing?
Um like the charges are the same or
Charges are the same, like what charges?
like it has a positive and a negative charge. Cause I think I remember saying that like what my teacher told me about how if it's neutral it means it doesn't have a charge, but then you said that's not true.
Hmm.
So
So we already had a conversation on it. So there must be some positive charge as well as some negative charge. And the
mhm.
magnitude of both of them must be equal. So that's why neutral is something which is supposed to be that the net charge on the body is zero. So
Oh.
this body has net charge zero, but it must possess some positive and negative charge. So how can
Mhm.
we induce electric field in such objects? What we can do is we just put it in a uniform electric field like that.
Mhm.
So if we put it in a uniform electric field, as it is a conductor, so it won't allow to field line to pass through it. So this is something which is not possible. In
Mhm.
respect to it, what would happen here is that automatically on this side there must be some positive charge, and automatically from this side there must be some negative charge.
Mhm.
And because of that positive and negative charge, there must be some electric field, which is something we call induced electric field.
Mhm.
And but in case of conductors, there is no induced electric field. But in case of dielectric, we do observe some electric field inside the object.
Mhm.
So that is something we say,
So
and it is also calculated by this relation.
so the reason that it's like going through is because it's positive on one side and negative on the other, right? Like if it had positive and positive, then you can't put a uniform electric field through it, right?
Now, understand it this way. You raise a very good question. If it has, now let's take all the cases. So there are multiple cases possible in order to understand it completely. Suppose there is no charge, Q is zero. So if there is no charge and Q is zero, what does it mean?
Mm-hmm.
It means it is an insulator or something which cannot conduct because for conduction charge is necessary.
Mm-hmm.
So how the field line will behave? They will pass through it. They will penetrate it and pass through it like that.
Mm-hmm.
So field line can easily pass through them if it is an insulator. Next thing, if it is neutral, like the case we think, if Q is not zero, Q net is zero, neutral. So this is something which is supposed to be happen. Positive must be gone through one side and negative must go through one side, and they will allow electric field lines to pass through their surface. Next case, if it is positive in nature, like you said, positive, positive. So we won't say it positive, positive. We'll simply say that this is positively charged conductor. So if it is positively charged conductor, then electric field line must try to push it. So about its center of mass, it just push it in the direction of field line.
Mm-hmm.
And if it is negative in nature, like Q is negative here, so you must say like in your terms negative negative on both sides. So it must be electric field force due to electric field, but it will be supposed to act in the opposite direction of the field line.
Mm-hmm.
Like here. So the whole object or the whole body would move in opposite direction of the electric field line. So this is how you can relate all the three cases or four cases.
Mm-hmm.
Movement in field direction, and here movement opposite to field direction. So this is what conclusion you can draw from the cases. All right, let's move on. Now just think of it and tell me what is supposed to be the answer.
Mm, one of them is positive and the other one is negative. But why does it matter which one's positive and which one's negative?
If there are two charges and one is positive and one is negative, then electric field line must originate from positive and terminate into negative. Understand it this way. And but here you can't say that electric field line are coming from somewhere, terminating into Q1, coming from somewhere, terminating into Q2. So they must be of same nature, first of all. And second, as electric field line is terminating into the charge, so they must be negative in nature. Because from positive charge, electric field line originates.
Oh,
But from negative charge, it terminates. This is what we just studied
oh,
right now.
yeah.
So both negative is the correct answer.
Mm-hmm.
Think of this and tell me.
Hmm. Oh, it's B.
So you are saying that electric field line must be passing through the object, and that too an uncharged sphere. So here, this
Isn't that
uncharged
what you drew
sphere,
like 2 slides ago? I think you drew like the electric field going through the
see,
that
in
figure.
this case, it is not able to terminate the object or the sphere. Here, it is passing through the sphere.
Yeah,
Here, it just bend.
yeah.
Here, it's steep in line. First of all, the question is asking that for this uncharged sphere. So the uncharged sphere doesn't mean that Q is zero. Q is zero. It means that it is neutral in nature.
Mm-hmm.
Uncharged means this neutral. So there must be something that we have to define here. And for this, we have the nature of the electric field lines. So electric field lines, first of all, never pass through the conductor. So B option is highly wrong. This is highly against, you can say, the basic behavior of conductor. Conductors will never allow electricity to pass through them. You can also remember it this way that whenever we are sitting inside a car and there is some thunderstorm lightning going on, so it was advisable that to stay inside the car. Don't go outside. Why?
Mm-hmm.
Because if the lightning strikes your car, it won't affect you at all. How? Because the whole charge is supposed to be moved from the surface through the earth. So
Mm-hmm.
if this is the conductor, so this is what is happening here. The whole charge, electric field line, it just passes through the surface to the another conductor. So there is no electric field passing through it. That is what the basic behavior of conductor is. So A, C, D. Now all of them can be possible. Now we have to think about it, how it is supposed to be. So this is highly wrong again, because electric field line is supposed to form curves. This is what we studied,
Yeah.
not steep lines. So it is not possible, and we have to neglect this as well. Now these are the two relations. Again, there is no curves. So if there is no curves, only the straight line, it is also wrong. C is the most appropriate answer. And
Um,
we just saw it in the previous slides, like how it is the answer. In this diagram,
mm-hmm.
like there is a conductor placed in a uniform electric field, the electric field line bends
Mm-hmm.
to the surface of the conductor, and there is no
Mm-hmm.
field inside. E inside is zero. So remember each and everything. Let's
Yeah.
move ahead. Now there is some mechanics question based on electric field line. Next, we are going to see that how a charged particle is going to actually behave in the electric field. Like you can say, if I place a charged particle here, so what is the trajectory it is going to follow? Like we know it is going to feel the force, it will displace. But what is the path of its displacement? So there are multiple cases in which there are different paths. So we're going to look at those paths. The case one says that the particle was initially supposed to be going there, and electric field is going to be in that direction. So the path of charged particle must be with the charged particle of with the electric field only.
Mm-hmm.
Like again, if positive charge is placed, its path of displacement will be along the direction of electric field, assuming that initial velocity is in the direction of electric field. The second case here, it can be that electric field direction is this and initial velocity direction is this. Then its path is going to be like that. First it go here and then it came back here. But in the very first case, it is supposed to be going there only.
Mm-hmm.
In second part, something like that. But in the first case, in the direction of field only. Another case we can have here, if electric field is supposed to be this way, charged particle has initial velocity in this direction. Then how we are going to see the path of the charged particle. So here, because of its mass, there must be some gravity acting on it towards the surface of the earth. It has some initial velocity in this direction. And if we consider the electric field also in this direction, the path of the charged particle is going to be something like that because of the gravity and all the things. If there is no gravity, only electric field, then path is going to be somewhat like this.
Mm-hmm.
Like it will also depend on the strength of force acting downward. If it is much force, displacement would be less. If it is less force, displacement would be more.
Mm-hmm.
Next case we have is if we have thrown that particle at an angle theta. Again, electric field is supposed to be this, downwards. Then the particle would go like that, something we call projectile. Again, there will be some gravity acting on the charged particle in the downward direction and electric force also in the downward direction. But its displacement or its initial velocity vector puts it in this path.
Hmm.
Acceleration with acceleration. This is one numerical we'll talk about. So next we have electric field for different objects, like how different objects possess different type of electric fields. So we are going to actually look at two things here. First, the direction of field that is originating from the different objects, and also what is the magnitude of that field which is originating from different type of objects. So
Hmm.
this is, you can say, all about electric field with different objects. First, it starts with point charges. So because of point charge, I already explained that electric field is supposed to be kq by r square. This.
Hmm.
Although you can also see that how we got it. We define the electric field that it is nothing but force per unit charge. We put the value of
Hmm.
force here and we got electric field as kq by r square. Then we have some electric field and R graphs. Like as the distance increases or decreases, field strength also changes. So how the electric field strength is going to get affected with the increase in length? This is what we're going to look next. So we know electric field is nothing but kq by r square,
Hmm.
and we have E as y-axis and R as x-axis. Then if we assume that there is a charged particle which is placed here, like at this point, we assume that at this charge here, force will be in some direction. So just assume that there is a test charge and electric field is also there. So how the force is going to act on it? That what is the direction of force? So direction of force will be in the same direction of electric field. This is what you need to understand as we saw it
Hmm.
earlier. Force will be in same direction of electric field.
In this case, what's the direction of the electric field?
In
Oh,
this
it's to the
case, the direction of electric, yeah, it is towards right.
okay.
Like this way, electric field is this way, so displacement is also going to be this way.
Okay.
So we have considered that right direction is positive.
Hmm.
So if there is a positive charge and it is being placed this way, so as the distance decreases, the electric field increases, but as the electric field decreasing because of the distance increase.
Hmm.
So this is what we saw as the graph or the variation between electric field and R. Or you can also see from this that E is inversely proportional to R square. This means if R increases a little, E would decrease very much because of the square factor. This is what we
Hmm.
called, and this side direction will be left.
Hmm.
So we assume it to be negative. Then field varies with R in this way.
Hmm.
So it is supposed to be going like that. So again, Based upon this, there are many questions which is already being asked in the exam. So we have to keep that knowledge of V versus R graph. Let's do a problem based on this. So the question says that five charges, each of magnitude plus q, are placed at the corners of regular hexagon of side A. So what do you mean by regular hexagon?
That has 6 sides.
That's it.
Um, like each side has an equal angle.
Yeah, equal sides and equal angles both.
Mm-hmm.
Whereas hexagon is six-sided figure. Find the magnitude of electric field at centroid O. So at point O, we have to find the direction of or and the magnitude of electric field. Now, how can we calculate it? That is the question. So because of this positive charge, where is electric field supposed to be? In which direction? Away from the positive charge, like in the direction of electric field only. Electric field must be this way
Mm-hmm.
at this point O
Yeah.
because of this P charge. Similarly, because of this E charge, electric field is supposed to be at this direction towards left.
Mm.
So can I say that because of this B and because of this A, electric field is going to cancel out each other?
No.
Yeah, they will. Because electric field due to E point and electric field due to B point must be same in magnitude, and the magnitude is kq by a square. So if the magnitude is equal and the direction is completely opposite, then what is the net field due to these two charges? It would be zero.
Mm-hmm.
So because of B and E, there is no electric field. Now let's see C and F. Because of this C positive charge, electric field is again supposed to be away from it.
Yeah.
And because of this F, it is again supposed to be away from it.
Mm-hmm.
So E net again due to,
And same thing with the with point A, right?
yeah, but in the opposite direction of pointer, there is no charge.
Oh, so C and F will cancel out.
Yeah. So again, because of this, there is no field. So we can say that out of the four, out of the five, because of the two, and the twos is CF and BE, there is no field. So there must be some field because of A, because in the opposite direction of A, there is no charge. Field must be in this direction, and its magnitude is going to be kq by a square,
Oh,
as the
that
distance between the charge and the point is a.
yeah.
So kq by a square. B
Mm,
option is going to be the correct one. Although it is more kind of, you can say, application-based question instead of a numerical, because we just have to analyze and check it out that which should be the force, electric field.
mm. Yeah,
So
that was an interesting.
eh, we do had so many questions practice. But again, courtesy of the class, we have to move on. A lot of things to cover.
Mm,
So the next part of this, you can say, lecture is electric potential energy. So that electric potential energy is again something that I explained you earlier. Whatever work is done against the electrostatic force, the work done will be stored as the electric potential energy. So you can explain it this way. Whatever work is done against the electrostatic force, it will be because of potential energy. There was the energy, that's why the work is possibly done. If there was no energy, then there wouldn't be any work against something like electrostatic force. So we'll see that how we define it. So electrostatic potential energy is something defined by the definition of what is potential. Potential is something which is denoted by V. It is scalar in nature and it is defined as work done per unit charge. Like V is nothing but work done per unit charge.
Mm-hmm.
Again, this V is what? This V is potential. This W is that work which must need to be done, and the Q is magnitude of charge. So this W which we supposed to use here to find potential is something potential times the charge. So
Mm-hmm.
this work is stored in potential energy. So this potential energy is something denoted by U, that is equals to delta VQ. Because potential is not defined, potential difference is defined. Whenever we are talking about the potential, we are actually talking about the potential difference, that is delta V. And that potential difference is
Mm-hmm.
always there due to, you can say, the electric field out there. And that electric field is somewhat out there due to the electric force. And the
Mm-hmm.
force is there because of the magnitude of the charge. So we can see these are the effects of the charge present there. And that's why we are studying everything because charge is something which is there in everything around us. So we have to define electric potential energy for multiple charges and how we would define it. Let me just give you a very simple basic trick. Remember it, this is something which we are going to use to solve the numerical thing. Suppose there are two charges, Q1 and Q2. They are separated by a distance. And the examiner asks what is the potential energy of this case. So we'll simply say that U is nothing but K Q1 Q2 by R. That is something, the formula of potential energy. Just remember it this way only.
Mm-hmm.
Case 2. If we had three charges, Q1, Q2, Q3, then what is the potential energy of the system? Assuming every charge is separated by the same distance A. Now, how can we solve this? So, remember that potential energy is something which exists between the pair of charges. So,
Yeah.
just find out the number of pairs you can actually obtain from the given set of charges. Like from this particular question, Q1 and Q2 can be a pair. Q2
Q1,
and Q1
Q2,
can be a
Q2, and Q.
Q2 and Q3 can be a pair.
Yeah.
So these are the possible pairs which are there. So potential energy
Mm-hmm.
is going to be, I guess it must be coming to your mind, K Q1 Q2 by A plus K Q2 Q3 by A plus K Q3 Q1 by A. This is the potential energy of the system.
Oh, okay. So you just add up like the pairs.
Yes,
Oh, and why do you divide it by A?
because the charges are separated by A distance. Like this relation has a proper derivation.
Mm-hmm.
Like how this relation came, how we are supposed to using this formula only. Everything has a reason here in physics.
Mm-hmm.
But if you discuss it in that much depth, it won't help us. Although for solving numericals, this is something which are going to use. So this is just a trick to remember the relation without knowing the reason that how it came.
Okay, got it.
Case 3. Let's make it more interesting. So there are four charges Q1, Q2, Q3, Q4, and all the charges are separated by a distance, like they are supposed
Mhm.
to be put in at edges of a square. So tell me what is the potential energy of the system?
So it would be KQ1, Q2 over A plus KQ2, KQ2, Q3 over A plus KQ3, Q4 over A plus KQ4, Q1 over A.
So this is going to be the potential energy of the system. So depending upon the number of charges, the system has different energy. But
Mhm.
here is the twist. This is not the completely correct, because you missed two more pairs. Like this is one pair, this is one pair, this is one pair, this is one pair, which you have given the equation for. What
Oh,
about these two pairs?
Q1 and yeah, I was gonna say the diagonal pairs.
All the pairs will contribute towards it. So as the number of charges increases, the value increases. Q1, Q3 by it now it's not A because we need to understand the length of the diagonal.
Mm-hmm.
If it is A, it is A. Using Pythagoras, can I find this diagonal?
Yeah,
And what the diagonal is supposed to be?
in this case, it would have been like A squared plus A squared equals the diagonal side squared.
Then what it is? Give me the final answer.
Uh, we don't have values though for it.
But we have A and A. So A square plus A square is something going to be the diagonal. So it is 2A square. So we just have to
Mhm.
square root it. So we got root 2 times A. So it is root 2A. So here we have to write root 2A
Oh,
here also. So this is going to be the complete energy.
mm-hmm.
Now, what is supposed to be the answer? Assuming Q1, Q2, Q3, and the distance is something again A. What is the potential energy of the system?
KQ1, Q2 over A plus
Yes,
KQ2, Q3 over A plus KQ3, Q1 over A.
exactly. So again, you don't have to think much about it. Let's do this one. So we'll assume that the system has three charges, and these three charges are same in magnitude and separated by a same distance. A.
Mm-hmm.
So again, in the system, how many pairs are possible?
The first and second, the second and third, and then the first and the third.
First, second, second, third, first, third.
Yeah.
So U is going to be K Q Q by A square. K Q Q by A. K Q Q by 2A.
Mm,
Got
yeah.
it?
Yeah, because it's double the distance.
Yeah. 2KQ square by A plus KQ square by 2A. So if you look at it properly, isn't it like 2 plus half?
Mm-hmm.
So it's like 2 plus half. So what is 2 plus half?
2.5.
In fraction, 5 by 2, kq square by a. This is supposed to be the potential energy of the system.
Mm-hmm.
Again, you tell me now the answer.
Mm. So it's KQQ over A. Oh,
The first four pairs which we are going to get, they are the same.
yeah.
So can I write
And
4 kq square by a?
yeah. And then
And
the
then for
diagonal.
diagonal, it is going to
Mm.
be twice of kq square by root 2a.
Mm-hmm.
So if I solve it, let me take these things common. I'll be having 2 plus 1 by root 2 inside.
Mm-hmm.
If I solve it further, I'll have 2 root 2 plus 1 by root 2. We can also divide this. So we'll get root 2 here.
Mm-hmm.
So root 2 kq square by a, 2 root 2 plus 1. That is our answer. Like
Mm-hmm.
once you get going, just keep going. Try to do
Yeah.
as many problems as you can so that this topic will become very easy. Total energy of the system. Again, this is the same question. Let's go ahead. How much energy is required to change configuration? Now, whatever work done of internal energy we found in these cases in the previous slides, that much amount of energy is required even to change its configuration, like from this to this. Like
Mm-hmm.
if I went from this to this. All right, this is important. Let's see this. So suppose if we have the charges placed in this configuration triangle earlier on, and later on we just put them in straight line. So how much energy is required to change the configuration? So there must be some potential energy of this system, the
Mm-hmm.
first one, and there must be some potential energy of this system, that is the second one. What we can do is we can calculate the potential energy for both the systems and subtract it. So that much amount of energy is required to change the configuration. Is
Mm-hmm.
the good? Okay. So U1 is going to be 3kq square by a square. I can write it directly now.
Yeah.
And for this configuration, I just wrote it earlier. It is 5 by 2kq square by a square.
Yeah.
So energy required is going to be delta U, which is supposed to be what? Change in the energies. That is 3 5 by 2 kq square by 2 minus 3 kq square by 2. So it is coming
Mm-hmm.
out as negative kq square by 2.
Mm-hmm.
As it must has lose some energy to become this second configuration. From first to second, it has lose energy. This is what
Mm-hmm.
this negative sign signifies here. When you're going to solve these questions for something like in terms of numbers, they are supposed to be more, you can say, critical. But when you're solving in terms of variables, they are more easy because
Yeah.
we have taken the similar variables and we are not actually putting their values.
Mm-hmm.
So just basic calculation. But the concept is again, it is important. Actually, we are not doing anything, something which is grade 12 level. We are simply subtracting two terms, two variables. But how these two variables are obtained, that is something we have learned in this class.
Mm-hmm.
How much work is required to change this configuration? So whatever energy we have find out, that much amount of work is required. Negative kq square by a. Work is also going to be the same. That is also you need to remember. Whenever there is work, there is energy, because without energy, there is no work. That's it.
Mm-hmm.
Simple logic. All right, try this one out. So when the separation between two charges is increased, the electric potential energy of the system or the charges will increase, decrease, it remains the same, may increase or decrease. Try to answer this question considering the relation of electric potential energy, which we just saw in various problems.
Mm, then the potential energy will decrease.
Correct. What was the relation? K Q1 Q2 by R. So U is inversely proportional to R. So if R increases, U must decrease.
Mm-hmm.
Remember the relation. So I guess this is something, the last part of the topic, last part of the lecture, potential. So which I just defined that it is nothing but work done per unit charge. Now, if you define it in a better way, that what potential exactly is. So what we have defined is, suppose there was some charge which was like at infinity, and because of that charge, there is some electric fields which are going through this like that.
Mm-hmm.
So this field is something which is because of some charge which is at infinity, and some field lines are passing through the space. So in this space, we just assume 2 points, like point A and point B.
Mm-hmm.
So in order to identify that which point is closer to the charge because of this which electric field is there, in order to find that which point is closer to the charge, source charge to be precise, we define potential. And that potential is something which is not defined for a point, but it is defined for 2 points, like the difference
Mm-hmm.
between the 2 points. So that potential difference between these 2 points is something like what work we have to do in order to move charge between point A and point B. So
Mm-hmm.
that is how we define the potential, like whatever work we are required to move a charged particle in some external field. So that work per unit that charged particle is something that the potential difference of the 2 points about which we actually moved.
Mm-hmm.
So it is not something which is easily understandable because here you have to assume a lot of things, you have to imagine a lot of things. You will
Yeah.
never see electric field lines ever in life, but because of those lines only, there are so many things which are going on.
Yeah.
But we can't see this, unfortunately.
It's just something to
Similarly,
like think about though.
yeah, although you can like draw them, you can like see them through some different source, but not in reality.
Mm-hmm.
So potential is defined for that thing only. So if there are, suppose, again four charges which are kept at the corners, and the examiner says what is the potential of the point O, and O is supposed to be the center of the square. This is like you can say a question. So potential is something which is work done per unit charge. What is work done? What we found K Q1 Q2 by R, and 1 Q is there, so 1 Q will cancel out 1 Q. So potential is something K Q by R. Now remember the formulas which we have seen so far.
Is it not
Like
KQ2 over R? Because you only canceled out one Q.
yeah, this Q2 is something which is question related. Like in the next question, you're going to understand why I have just removed that two thing
Oh,
because it
okay.
is not fundamental. Yeah, Q2 is not fundamental. So in the relation, we just put KQ by R because potential is something which is due to one charge, single charge. So
Mm-hmm.
as far first we see electrostatic force, which is KQ1 Q2 by R square. Then we see electric field, it is KQ1 by R square.
Mm-hmm.
Then we see potential energy, which is KQ1 Q2 by R.
Mm-hmm.
And now we are looking at electrostatic potential, which is KQ1 by R.
Okay.
So this thing has five quantities, this thing has four quantities, this thing has four quantities, and this thing has only three quantities.
Mm-hmm.
So you can learn their formulas by just remembering that thing because
Mm-hmm.
sometimes it is really confusing that what was which include
Yeah.
Q1, Q2 both, which include nothing. So that
Yeah.
is
This is
something
helpful to see that there's like these four.
because these are very similar relations, right?
Yeah.
Like between E and V, sometimes people or students get confused.
Yeah.
So suppose that this is the center of the square and square supposed to has four charges at its corners.
Mm-hmm.
So if we find the net potential at O point, it is supposed to be potential due to each charge.
Mm-hmm.
So we can write that net potential is something V1 plus V2 plus V3 plus V4. Now we have to find at the center. So we have to find the distance between this charge Q and the center. We know
Mm-hmm.
that the diagonal is root 2a. So what is half of diagonal?
Um. You just square it. So wait, no. Um. Yeah.
So it is going to be root 2a by 2. So root 2 will cancel out 2 and it becomes root 2. So a by root 2 is something which is diagonal. So it is going to be
Mm-hmm.
kq by a by root 2 plus kq by a by root 2 because every charge is same. So every potential is also the potential due to every charge is also going to be same.
Mm-hmm.
So it is going to be 4 root 2 kq by a. So that is
Mm-hmm.
how V net can be obtained. Net potential. So remember the relation. Why we can apply this? We can apply this because vector, it is not vector. If it is a vector, we wouldn't have applied this. We
What's a
can't
vector?
apply it. Okay. Vector is very important thing. Vector is something basically a type of physical quantity it is. Like physical quantities are basically of two types. One is scalar and other is vector. Scalars are
Oh.
those which have magnitude only, and vectors are those which have magnitude as well as directions. So
Okay.
potential is something which doesn't have any direction, so we can simply add them. But the other
Mm.
quantities like electric field, electric force, these are vector quantities, so we have to see their directions as well. So we cannot add them directly like this.
Oh, okay.
So this is what it is written here. Potential
Yeah.
is scalar, and because of this only, the
That's why you can.
summation of all these potentials due to charges is nothing but the total potential of the system. But
Mm-hmm.
net electric field is something which cannot be found out by this relation.
Mm-hmm.
Now just try to rank these three situations. No, one second. It is something else. This is A point. This is B point. This is C point. And what you have to do is you have to rank these 3 points according to their net electric potential produced at by the 2 points, which is two protons. So these two charges are nothing but protons. So
Mm-hmm.
this is, you can say, E plus. It is also E plus. These are E plus. Potential is what? Proton is what? Which is represented by E positive. Electron
Yeah.
is what? Which is represented by E negative. So we can write it directly here. E plus. So let us try to find out for the first configuration. VA I can write it as, so it will be KQ. Q is E by what? Distance. Distance is, what is the
Um,
distance? We can
like,
assume to be the same distance like A and 2A.
mm-hmm.
Like A, 2A.
Mm-hmm.
A, 2A. We can assume it. This is
Mm-hmm.
2A, this is A.
Oh, okay.
So it is going to be 3 by 2 K E by A. This is VA, like potential in the first question, first
Mm-hmm.
part. Now VB, again it is going to be 3 by 2 K E by A.
Mm-hmm.
And in VC, again it is going to be 3 by 2 KQ by A. So
They're all equal.
yes, because potential is something which doesn't depend upon the direction. So as it doesn't depend upon the direction, so we can say that it is equal in every point, on every point,
Mm-hmm.
produced by these protons. Now there is this relation between potential and field. What is electric field? KQ by R square. What is potential? KQ by R. So from this field, if I write it this way, can I replace V in place of KQ by R?
Yeah.
Can I write that E is nothing but V by R?
Yeah.
So this is what the relation between potential and field.
Mm-hmm.
Let us see how they show the variation. V is KQ by R. If we assume that the relation, so electric field and potential going to be positive. Electric field due to positive and negative charge. Potential varying with respect to displacement is something like that, like this. So for positive charge, the potential is going to vary with distance. Like this is R, this is potential. So
Mm-hmm.
as
Mm-hmm.
distance increases, potential decreases a lot. And for negative charge, it is opposite.
Mm-hmm.
V dash, again same thing. As R increases, potential decreases to 0.
Mm-hmm.
If there are multiple point charges, as I said, just add all the potentials like this. Whatever number of charges are there, just add the potential due to all the charges.
Mm-hmm.
Now, this is the last thing of this chapter, that is equipotential surface. So, equipotential surface is something, those surface at which potential is
Equal.
equal throughout. Those surface at which potential is equal throughout. Like suppose this is some positive charge. Because of this positive charge, I just draw a sphere around it, and this sphere is supposed to be a distance away from it. So at
Mm-hmm.
every point on this sphere,
It's
potential is
equal.
supposed to be kq by a.
Mm-hmm.
That
The
is
distance is
equal.
equal.
So that surface is something which is called equipotential surface.
Got it.
So for different configurations, equipotential surface is something different in
Yeah.
configuration. So that's it for the today's class, and this is what we're supposed to
I think this